This is a description of the Duo 128 Elite architecture. If you are not interested in computer architecture, then I would not recommend you watch this video because it will bore you out of your mind. But if you are interested in how the Duo works, this video will provide lots of in-depth information. To begin, I will explain some terminology that some of you may not be familiar with. You probably already know that a single bit is a 1 or a 0, represented by the circle that you see in this diagram. A nibble is a rare term that refers to a grouping of 4 bits. This is relevant to the Duo computer because it is a 4-bit architecture, so you'll see the word nibble used a lot. The term nickel, which is even more esoteric than the term nibble, refers to a grouping of 5 bits. The next set of slides will show each of the general regions of the Duo computer. The first region contains 256 nickels of ROM. This includes an EEPROM and its address counters, which will be described later. The ROM stores the program for the computer to run. The command parser determines how the current command should be loaded. The current command is stored in the command registers so that it can be executed. The arithmetic logic unit, or ALU, accepts the arguments of the command and performs a set of calculations. The output of these calculations is fed into the destination selector. This set of chips selects a calculation and its appropriate destination based on the current command opcode. The graphics processing unit, or GPU, displays graphics on the 8x8 LED matrix. Random access memory, or RAM, stores data that the computer can use and manipulate. There are 64 bits of RAM, or 16 nibbles. Lastly, the processor clock governs the timing of all operations in the computer. Now I will describe each general region in greater detail. First, ROM and Address Chips. The ROM chip itself actually contains 2 kilobytes of memory. The computer only accesses 256 nickels at a time, so 8 blocks of the ROM can be allocated for 8 different programs. 2 synchronous 4-bit counters determine the current address being read by the computer. Before the 8-bit address is fed into the ROM chip, it passes through a tri-state buffer. The output state of the buffer is controlled by a front panel switch. When the buffer is set to high impedance, the ROM address may be manually selected by front panel switches. This feature is used when programming the computer. Command parser. A 2-nibble to 1-nibble multiplexer, abbreviated as MUX, determines what data should be fed into the argument registers. The argument registers will be described later. Recall that the ROM outputs a nickel, or 5 bits. The first bit is called the prefix bit, while the remaining 4 bits are the data nibble. When the prefix bit is 0, the ROM data nibble is stored in the current argument register. When it is a 1, the data in RAM is stored in the argument register instead. This allows commands to call a variable to substitute any of its arguments. To send write signals to the argument registers, the command parser uses a 1-bit to 4-bit demultiplexer, abbreviated dmux. The address of this dmux is determined by an argument's remaining counter. As the computer loads each argument, the argument's remaining counter is decremented. The number of arguments is initially determined by the first opcode bit. Command registers. There are 3 argument registers, each containing 4 bits. As described earlier, the source of the argument registers is determined by the command parser. The command registers also includes a 4-bit opcode register. This determines the type of command being executed. Lastly, the conditional bit register determines whether the current command should be conditionally ignored. This bit is loaded simultaneously with the 4-bit opcode. Arithmetic logic unit. Some commands do not require any manipulation of data. For example, the write command copies the given data to the given address. No chip performs calculations in between. The goto command is another example. It copies an address from arguments into the ROM address counters. The output command copies data into the GPU, which will be described later. The input command is the last command which performs no ALU calculation. There is one unused argument in this command, which could potentially be used to access a larger array of buttons. The add command uses a 4-bit full adder to add two given numbers. The computer has three bitwise commands. Bit on sets a single bit in a nibble to a 1, bit off sets a bit to 0, and bit get retrieves a bit. The comparison commands equal, unequal, and greater use the magnitude comparator chip. Destination selector. The destination selector uses three 2-nibble to 1-nibble muxes to feed one of the 6 ALU operations into the RAM. The address of these muxes is determined by the opcode. To send a write signal to the appropriate destination chip, the destination selector feeds the opcode into a 1-bit to 16-bit dmux. The output of the dmux is processed by various gates and translated into a write signal to one of 4 locations. If you are curious about the specifics of these gates, please consult the schematics. An additional set of gates decides which of the 3 magnitude operations should be fed into the Boolean bit register. This register is located in the processor clock. Random access memory. The RAM chip itself consists of 16 nibbles. Depending on the processor clock step, the RAM address may either be the ROM output data nibble or the ALU output. The ROM output is used as the address when substituting variables for arguments. Because the RAM chip's data output pins are also its input pins, a 4-bit tri-state buffer sits between the RAM chip and the output of the destination selector. This buffer is only active when writing data into the RAM. Graphics Processing Unit. A 64-bit VRAM chip stores the pixels which are constantly dumped onto the display. The display is an 8x8 array of diodes and can only display one row of pixels at a time. The output of the VRAM is 1 byte wide. Each of the 8 bytes encodes one of the rows on the display. An 8-bit tri-state buffer is used to write data into the VRAM. When data is not being written, the buffer's output is set to high impedance. A 2-nibble to 1-nibble mux determines which address to feed into the VRAM. When writing data into the VRAM, the mux selects the ALU output. Otherwise, it selects the VRAM address counter. The LED display accepts 1 byte to select a row, and a 2nd byte to determine the data to display in that row. The output of the VRAM determines the data to display in the selected row. A 1-bit to 8-bit dmux is used to select the row. The VRAM address counter simultaneously provides the dmux and the VRAM chip with a 3-bit address. The counter is incremented quickly from 0 to 7 in order to refresh all the rows on the display. Processor clock. The processor clock begins with a simple 555 timer chip which generates a square wave. The speed of this chip can be modified by front panel switches. The timer controls a decade counter, which cycles through one of 4 outputs. The first of these outputs increments a processor clock step counter. This chip determines which of the 6 clock steps is being executed. The third output of the decade counter is used to pulse the output of a 1-bit to 8-bit dmux. The step counter provides the dmux with an address. Some miscellaneous gates process the output of the dmux and the step counter to provide the output of the processor clock. The Boolean bit and conditional bit registers interface with these gates to conditionally inhibit a command's execution. A command is ignored when the Boolean bit is 1 and the conditional bit is 0. Clock steps. 1. Write the ROM output into the opcode register. 2. Increment the ROM address counter and set the argument's remaining counter. The clock now enters a loop in which it loads a certain number of arguments into the argument registers. 3. Write the ROM output into one of the argument registers. 4. Increment the ROM address counter and decrement the argument's remaining counter. 5. If the argument's remaining counter has not decremented below 0, go back to step 3. If the last step was not executed, all the arguments have been loaded. 6. Send a signal to the destination selector to execute the current command. This concludes the explanation of the Duo Elite computer architecture. Thanks for watching.